A bridge strong enough for trucks was built in China in about 1 week by a small crew, using a material the construction world once dismissed as fit only for huts. When the bridge was finished, trucks drove across it. A few years earlier, engineers in China completed what is now recognized as the world's first 7-story building made primarily from that same material. It grows back in under 10 years. It locks away carbon as it grows. And technically, it was never even a tree, a grass. What you are about to see is not a laboratory experiment or an architectural concept. It is full-sized buildings, real bridges, and a national industrial plan already changing how an entire country builds. And the strangest part of this story is that the answer was sitting in plain sight for almost 40 years before anyone with real money decided to take it seriously. Stay with us through the end, because the final chapter of this story is the one that tells you where the rest of the world is about to find itself. The proof is already standing. Let us start with what China has already built, because the scale of it is the thing that stops engineers cold when they first encounter the numbers. The 7-story building is not a one-off. It is a proof of concept executed at full structural scale, with real occupants, real load calculations, and real code approval. The columns, beams, and floor systems are prefabricated components assembled on site the way a steel frame goes together. Precision manufacturing done off-site, structural connections made at the building. 7 stories, load-bearing, occupied. The bridge in Hunan told the same story from a different angle. One engineer, working between universities in China and the United States, designed a vehicular bridge from prefabricated components. A small crew assembled it in approximately 1 week without heavy equipment. When the bridge opened, it carried trucks not ceremonially, but as working infrastructure, doing the job that a concrete or steel bridge would normally do. But these visible structures are the edge of something much larger. In 2022, China partnered with the International Bamboo and Rattan Organization to launch a global initiative with a direct name, Bamboo, as a substitute for plastic. Chinese national leadership publicly backed the program and tied it explicitly to the country's formal climate commitments. The following year, China released a 3-year national plan to scale bamboo as a structural replacement for steel and concrete, including the establishment of demonstration zones across the country to prove the industrial model could work at. Volume. China holds approximately 1/5 of the world's total bamboo resources and has spent decades building the industrial chain to process them. Fiberizing equipment, resin treatment systems, hydraulic pressing facilities, quality certification infrastructure, and export supply chains. According to Chinese government figures, the country's bamboo forests absorb and store around 300 million tons of carbon annually simply by existing and growing. The financial target attached to this vision, 700 billion yuan by 2025, scaling to 1 trillion yuan by 2035. When a government puts numbers that size on a material, the rest of the world starts paying attention. Researchers who mapped structural bamboo companies globally found that roughly 2 in 3 were based in China, but they also found new operations appearing in the United States, India, Indonesia, Vietnam, Singapore, and across South America, where large native bamboo species are beginning to look less like background vegetation and more like a strategic resource. China did not make this bet because bamboo looked interesting. It made the bet because the materials that built the modern world were beginning to run into a problem they could not solve. The material that could not keep up. For 10,000 years, wood was the material that built the world. Every house, every bridge, every ship started with a tree. Wood is warm, workable, and strong enough to carry serious structural loads. Anyone with basic tools and enough time can shape it into almost anything a builder needs. But wood has a problem that the modern world has made impossible to ignore. It is slow. A Douglas fir ready for structural use takes 50 to 80 years to reach maturity. A hardwood like oak can take longer. A tree planted today might not be ready to build with until your grandchildren are adults. And the world is not patient. Cities are growing faster than at any point in human history. The demand for construction materials is not leveling off, it is accelerating every decade. So the industry turned to steel and concrete, manufactured at scale, consistent in their properties, available in whatever quantity a project requires. The shift made economic sense. It made logistical sense. And for several decades, the environmental cost was treated as someone else's problem. That accounting has changed. Steel and concrete production together account for more than 15% of all carbon dioxide humans release into the atmosphere every year, more than the entire global aviation industry. Every bridge poured, every high-rise framed in steel, Every highway resurfaced adds to a carbon account the planet is increasingly unable to absorb, and so builders found themselves trapped between two bad options. The slow material wood and plant-based alternatives is gentle on the climate but cannot keep pace with the speed of modern construction. The fast materials, steel and concrete, can keep pace but are accelerating a problem that is already reshaping the economics of building in coastal cities, flood zones, and heat-stressed urban centers where the consequences of that warming are arriving ahead of schedule. For a long time, there was no third option. You either built slowly and sustainably or quickly and expensively, in every sense of the word expensive. The third option had been growing in plain sight for millions of years. The problem was not that no one had seen it. The problem was that serious engineers had already decided it did not belong in serious buildings. The grass engineers laughed at. The plant is bamboo. And the first thing most people get wrong about it is the most basic thing. Bamboo is not a tree. It is a grass technically in the same biological family as the lawn growing outside your window, just scaled up to proportions that make the comparison feel absurd. Some species grow more than a meter in a single day. If you sat beside a fast-growing culm in the right season and watched carefully, you could see it moving. While a structural timber tree takes decades to reach usable maturity, bamboo gets there in 6 to 9 years. And because it is a grass, cutting the culm does not kill the plant. The root system, the rhizome network underground, stays alive and sends up a new stalk from the same base. No replanting, no waiting for a hillside to recover. The same ground that produced this year's harvest is already working on the next one. People across Asia understood this for thousands of years before modern engineering existed. They built homes, aqueducts, suspension bridges, and scaffolding from bamboo in ways that trusted it with human lives. Workers in Hong Kong and other dense cities still use bamboo scaffolding on high-rise construction today, ding structures dozens of stories above the street on a material that grows back before the building they are working on is even finished. Pound for pound, bamboo can handle tension forces better than steel. Its raw tensile strength is more than double that of ordinary structural wood. The plant that the modern construction industry called a hut material was, by the physics, a serious structural candidate. And the construction industry knew this. That is the part of the story that does not sit comfortably. The strength data existed. The fast growth was documented. The carbon sequestration was measurable. And the engineering establishment still spent most of the 20th century treating bamboo as something that belonged on the margins of serious construction, useful in places where nothing better was available, irrelevant everywhere else. So the real question is not why engineers failed to notice bamboo. They noticed it. The real question is why they still refuse to trust it, why bamboo was never trusted. The nickname that stuck to bamboo for most of the 20th century was the poor man's timber. It appeared in development reports as a solution for low-income housing in places where real materials were too expensive to import. It showed up at architecture schools as an interesting exercise in sustainable design. It almost never appeared in the load calculations of a building that needed to meet modern structural codes. And the dismissal was not unfair. A natural bamboo culm is hollow, which creates serious problems for structural connections. Modern construction depends on reliable joinery, bolts, brackets, fasteners that transfer load between components. Drive a bolt through a hollow bamboo culm and it tends to split along its natural grain. The hollow geometry that makes bamboo light also makes it structurally awkward at precisely the points where buildings need their components joined. The culm is also round, in a construction world built around flat, square, standardized dimensions. Every beam, every column, every joist in modern construction is sized, cut, and specified in consistent rectangular cross-sections that fit together predictably. Round bamboo does not fit that system. And then there is the variation problem, arguably the most serious one. One culm harvested from a given plant on a given day might test impressively strong. Another culm from the same plant, cut the same week, might be significantly weaker. The strength varies with age, with position on the plant, with growing conditions. There is no way to know from the outside which culm is which. For a structural engineer, that inconsistency is disqualifying. The approval system that governs what materials can go into a school, a hospital, or an apartment building is built entirely around certainty. A material must perform identically within defined tolerances every time, in every climate, at every point in the structure's designed lifespan. A material that might be strong is not a material that can enter a load-bearing calculation. Add to this bamboo's tendency to rot in sustained humidity, its vulnerability to insect damage if left untreated, and the absence of decades of testing data that code bodies require before approving a new structural material, and the engineering world's 100-year dismissal starts to look less like prejudice and more like a professional community responding rationally to genuine constraints. The breakthrough came only when engineers stopped asking how to preserve bamboo and started asking what would happen if they destroyed its shape completely. The idea that rebuilt bamboo. For most of bamboo's modern engineering history, researchers tried to make it work by treating it like wood. Cutting culms into flat planks, laminating thin strips side by side into wider boards, shaping it into forms the construction industry could recognize. The results were incremental improvements over raw bamboo, but they preserved the fundamental problems. The hollow structure was still a constraint. The natural variation between culms still introduced inconsistency. The material was still recognizably bamboo, with bamboo's limitations embedded in its form. The idea that broke the deadlock was simple and radical at the same time. What if you stopped trying to make bamboo work as bamboo and treated it instead as raw fiber to be rebuilt into something new? That question led to a process called bamboo scrimber, and once you understand the process, the results make complete sense. It begins with whole bamboo culms, including the bent ones, the thin ones, the pieces that would fail any quality inspection for conventional bamboo products. Instead of cutting usable sections from variable material, machines feed entire culms through a step the industry calls fiberizing. The culm is crushed and pulled apart along its natural grain until what comes out the other side is not bamboo in any recognizable form. It is a loose, stringy mass of raw fiber, something closer in appearance to rough straw than to any structural material. At this point, every weakness bamboo ever had has ceased to exist. The hollow center, gone. The round shape, gone. The variation between culms, gone. The tendency to split under fasteners, gone. Because the original form of the culm no longer exists. What remains is fiber, the strong part of the plant, separated from the structure that made it difficult to use. Workers dry those fibers, saturate them in resin so they will bond under pressure, and align them in the same direction. The aligned fiber mats then go into a hydraulic press, not a gentle compression, but extreme pressure combined with heat, forcing out the trapped air and consolidating the material into a dense, uniform block. What comes out does not look like bamboo. It looks like premium hardwood. It is heavier than water. Its surface hardness exceeds most commercial hardwoods, and its structural numbers are the ones that make engineers stop and read the data twice. High-quality bamboo scrimber has tested with compressive strength above 160 megapascals and bending strength exceeding 300 megapascals. Structural steel typically yields around 250 megapascals. A grass that regrows from the same root system in under a decade, processed into a material that performs in the structural range of steel. The manufacturing efficiency adds another dimension to the economics. Roughly 80% of the original bamboo input ends up in the finished product. The bent culms, the thin culms, the pieces that traditional bamboo processing would discard in scrimber production, almost everything becomes usable fiber. The plant that was already cheap to grow became cheap to process as well. But there is a brutal difference between proving a material is strong and convincing the world it is safe enough to build lives around. How bamboo entered the rulebook. The science behind bamboo scrimber is not new. The first high-strength version of this material was developed in 1987 at Nanjing Forestry University in China. The chemistry has been understood, refined, and published for nearly 4 decades. What changed was not the material. What changed was the world's willingness to build the systems around it. Having a strong material sitting in a lab is impressive, but it does not change the world on its own. The real obstacle that decides whether a material becomes a global industry is something that sounds boring but carries enormous weight: the building code. Building codes change slowly on purpose. The cost of getting a structural material wrong is not just about money, it is about buildings staying standing. An engineer cannot specify a new material for a school or a hospital just because one study says it seems strong. There needs to be years of testing, agreed international standards, and a clear paper trail that any inspector anywhere can check and trust. For most of bamboo's history, that kind of proof simply did not exist in sufficient depth. And even today, a gap remains. When researchers recently studied companies making structural bamboo products around the world, they found that only about a third published clear information about how strong their products actually were, and even fewer held basic environmental certifications. If you are an architect trying to specify this material on a real project, that lack of transparency is a genuine problem. You cannot build something important on numbers nobody is willing to show you. But that gap is closing, and it is closing fast. In the 10 years leading up to 2024, nearly 7,000 peer-reviewed studies on engineered bamboo were published. Rigorous mechanical testing, long-term performance data, fire behavior analysis, seismic loading experiments, the kind of accumulated evidence that building codes are actually built on. Engineered bamboo is now being evaluated against the same international standards applied to structural timber. Architects in Europe, North America, and across Asia are submitting drawings that specify bamboo scrimber in load-bearing applications and receiving approval. The material that spent a century being dismissed did not change its chemistry. It accumulated evidence. And once that evidence crossed the threshold that engineering institutions require, a door that had been closed for 100 years opened faster than most people in the industry expected. 40 years of science, 1 decade of critical mass, and a material that has now earned its place in the rulebook the construction world actually uses. But just as bamboo finally entered the rulebook, another question appeared, one that every new green material eventually has to face. How clean is it once industry gets involved? The catch nobody should ignore: bamboo scrimber is not a pure natural product. It is held together by synthetic resin, typically phenolic resin, which gives the final material its water resistance, dimensional stability, and binding strength. That resin is also what makes the material more complicated than it first appears. Engineers are still studying how scrimber behaves in fire over extended durations, how the resin fiber bond holds up after decades of cyclic structural loading, and what realistic end-of-life options look like when a building using this material is eventually demolished. These are not reasons to abandon the technology. They are the legitimate open questions that responsible engineering requires answers to before a material enters widespread use in schools, hospitals, and high-rise residential buildings, where the consequences of getting it wrong are not absorbed by a test sample but by people. The geographic gap is a harder problem, and in some ways a more consequential one. The countries that could benefit most from a fast-growing, low-cost structural material are frequently the countries furthest from the industrial infrastructure needed to produce certified bamboo scrimber. Converting raw bamboo into structural beams requires fiberizing equipment, controlled resin saturation systems, calibrated hydraulic presses, and quality testing capacity. China built that industrial chain over several decades with sustained investment. A country with abundant bamboo forests and no manufacturing base cannot replicate it quickly or cheaply. Think of the places where bamboo grows most abundantly across equatorial Africa, Southeast Asia, South Asia, and Central America. Regions building rapidly. Regions where a structural material that regrows in under a decade could genuinely change what gets built and who can afford it. These are also, almost uniformly, the regions with the least access to the machines that turn raw culms into certified building components. The gap between where bamboo grows and where it can currently be processed into a certified beam is the real constraint on how fast this technology spreads globally. But here is what makes that constraint interesting rather than simply discouraging. It is no longer a science problem. The chemistry is solved. The performance data exists. The code pathway is established. What remains is investment, supply chain development, and policy, exactly the kinds of problems that have been solved before in other industries, when the economic case became strong enough that capital followed. And the economic case is strengthening every year. Carbon pricing is expanding. Environmental regulations on steel and concrete production are tightening in major markets. Construction firms with sustainability mandates are actively seeking materials that sequester carbon rather than release it. A structural material that grows back in under a decade, stores carbon inside the building it becomes part of, and now performs in ranges that challenge engineered wood. That material has a commercial argument that did not exist 10 years ago and is becoming harder to dismiss every construction season. And that is where the rest of the world now finds itself, not at the beginning of a scientific discovery, but at the beginning of an industrial race. For thousands of years, building bigger meant cutting down something that took a lifetime to grow back. This is the first time we have a serious structural material that grows back before a child finishes primary school. That is genuinely new. And it is already holding up real buildings, carrying real trucks, and changing the calculations of real engineers on real projects in real cities. If this changed how you see the next building you walk into, hit like it tells us to keep making videos like this. Subscribe and turn on notifications so you do not miss what comes next. And drop your answer in the comments. If a plant that experts dismissed for 100 years turned out to be this powerful, what else do you think we might be overlooking right in front of us? This is Brightcore. Thanks for watching, and we'll see you in the next story.